interest of time, I'll just quickly introduce you. Chih-Chi, you're currently at Princeton, and you've been working on AllSky now in both in your PhD and your current work. And currently we have a talk on variational bias correction. So please go ahead.
Okay, thank you, Alan.
Thank you.
Yeah, thank you for and other committee for giving me this chance to present my work at GFDL. So I'm going to focus on variational bias correction. Okay. So to make effective use of satellite observation in DA, it's crucial to accurately correct their biases. In particular, some of these biases can be large, even larger than the amplitude of useful signals. However, these biases can be complex and state dependent, making them difficult to quantify. And these biases can also change over time, and they can be different, even for the same type of instrument. They can have different biases across different satellites. And currently, many operational systems use the variational bias correction, VarBC, to adaptively determine the bias within the variational DA framework. And on the left shows the cost function with VarBC capability. And in the observation cost function, JO here, the observation is compared to the bias corrected model counterpart, H tilde, which includes the output from radiative transfer model along with the bias correction predicted by VarBC. And typically this bias correction is expressed as a linear combination of predictors and associated with these coefficients. Specifically, the constant term is referred to as global offset because it will be important in my presentation. For VarBC, the VarBC coefficients beta here serve as additional control variables and are optimized along with the state X during DA. So which means that the estimated bias correction is also adaptively determined by these coefficients in each DA cycle. And the effect of VarBC can be understood by this normalized O minus by the O minus B normalized by the observation error variances. And this quantity measures how strongly we force the model to match the observation. So I'll refer to it as observation forcing from now on. And essentially what VarBC does is to adjust this O minus B, and therefore the observation forcing is also adjusted accordingly. So the advantage of VarBC not only lies in its technical convenience, but also in its ability to better distinguish between model and observation bias. The key reason comes from the use of anchor observation, which is the observation that is believed to be unbiased. Specifically, VarBC can leverage these anchor observations to better constrain the model state, providing a more accurate, ideally unbiased X as a reference. And then VarBC is then in a better position to estimate the observation bias to adjust the beta and more accurately based on this relatively unbiased model state. Here are a few examples of anchor observations. However, many of these anchor observations are still sparse in time, although we have RO observation that are well distributed, but their errors tend to be larger in mid to lower troposphere. As a result, anchor observations can help VarBC distinguish between model and observation bias, but they are not uniformly available across all regions. And in addition, the transition from clear sky to AllSky DA is likely to introduce additional complexity for bias correction. This is especially for channels that are sensitive to mid to lower troposphere, where anchor observation may be limited. And in addition, there is divergence in approaches to AllSky radiance bias correction. For example, including Claudian precipitation can make the bias more state dependent. And some show benefits from including cloud predictors, like as mentioned by proposal, especially for all sky infrared DA. On the other hand, some also suggest that it's not necessary to include this cloud predictors, especially for all sky microwave radiances. I mean, some include them while others do not, and this can be kind of explained by the fact that because we often assign larger observation error variance to cloudy scenes, so which means that the larger observation error variance reduce the impact of bias correction for those cloudy conditions. So it might not be necessary to include this cloud predictor for bias correction for cloudy conditions. But anyway, there is kind of some divergence in approaches. And in addition to the cloud predictors, there is also divergence in approaches regarding which subset of data are used for bias estimation. Again, some only use clear sky data, and probably because of this error variance normalization effect for cloudy schemes, and while some include cloudy data as well. So here's an example by Zhu et al. They propose to use both clear and cloudy data, but exclude samples with cloud mismatch because cloud mismatch may indicate large errors in the model state. So removing them for bias correction can prevent potential model error contamination. Specifically, in their scheme, samples are used if both model and observed cloud amounts are either above or below a predefined threshold, as shown by this figure, by the blue and green square here. And essentially, this approach, although it doesn't really utilize anchor observation, but essentially it uses cloud information as I kind of call it indirect anchor, but in a more passive way to exclude samples that potentially have large model errors. So the motivation of this work is to further explore using cloud information as indirect anchor for all sky, but I'm going to focus on microwave, specifically MCOA and ATMS bias correction, and with focus on channels sensitive to mid to lower troposphere, and also try to understand the impact of all of these divergence approaches, and also assess the impact of different VarBC strategies on whether a global weather forecasts. So here is the experiment setup. So I'm using the SHIELD model. This is a global forecasting model based on F3 dynamic core developed in GFDL NOAA, and SHIELD has been coupled with GSI. The core DA method, we use a hybrid 40 VAR, and this is configured to closely match GFS version 16.2. For faster testing, we are running this at reduced resolution. We run 2 months global cycling DA experiment with DA every 6 hours from June to August. And for the observations, almost all observations assimilated into GFS, including satellite and conventional observations, are also assimilated into SHIELD, except for a few high peaking satellite channels due to the lower model top of SHIELD. And in this study, we test the changes in DA setup for assimilating all sky microwave channels in MCOA and ATMS for the following channels, and the DA setup for other observation remain unchanged. So first of all, we looked into the control simulation where the DA setup is using the default. And by comparing the short range forecast to the conventional humidity observation, we found some dry bias in low level. And we also compared the forecast to MCOA and ATMS window channel observations. And these window channel observations have sensitivity to low-level humidity. In particular, colder brightness temperature indicate a drier low-level atmosphere. And the lower right figure shows the mean difference between the model and observation before and after bias correction. And it shows that the model brightness temperature are cooler than observation, suggesting the model is drier than observation, which is consistent with what we see from verification against conventional observations. And one thing to note is that VarBC reduces the magnitude of this mean difference between model and observation. In other words, VarBC reduces the observation forcing that could have been used to moisten the low-level troposphere. So given this dry bias, we question whether the current VarBC setup might be overcorrecting the bias, potentially masking part of the model dry bias signal. So to better understand, we investigate how observation affects VarBC, but specifically here, we only look at how observation affect the global offset, because we found that this global offset plays an important role. And the figure on the right shows this gradient of cost function with respect to global offset as a function of modern observation cloud. And the red means that the samples over this region tends to increase the global offset, and the blue means decrease of global offset. And note that to understand the change in global offset, it is actually determined by the summation of gradient from all the observations. So to infer the total change, we need to take a weighted average of this gradient, where the weights are based on how often these samples appear. So the white contour here shows the data frequency, and we can see there is an asymmetry. Specifically, there are more samples in the red area above the diagonal line than the blue area below, which suggests that the current VarBC scheme, if all these samples go into VarBC for bias estimation, we tend to increase the global offset, therefore increase the total bias correction. So these asymmetry in data frequency may explain the overcorrection of bias we saw earlier. So in GSI, the data used for bias correction actually follows the method from Zhu et al. Mentioned earlier. And from what we saw earlier, this data control may be too lenient for cloudy cases. Specifically for this yellow shaded area, this is where we observe asymmetry in data frequency. So which means that allowing these data affect bias correction might lead to the over bias correction that we saw earlier. So this motivates us to explore stricter data control to try to minimize the effect of this asymmetry. The first approach we try is to impose additional control on cloudy data. In particular, we only use samples when the model and observed cloud amount are reasonably close. We call this clear cloud experiment. And the second approach we tried is to completely exclude cloudy samples, and we call it clear experiment. So here we examine the time series of VarBC global offset, this constant coefficient in the dashed line, and the total bias correction in the solid line. And each color represents a different experiment: black for control, blue for clear cloud, and gray for clear experiment. So first, we observed that most differences in total bias correction shown in solid line comes from changes in global offset. So for example, the blue dashed and solid line are about like around 0.5K lower than their black counterpart. So this suggests that different data control affects the total bias correction via the change in global offset. And in addition, we see that both clear cloud experiment in blue and clear experiment in gray decrease the global offset, and thus the total bias correction. This is as expected because they both try to minimize the asymmetry effect. And the decrease in total bias correction means that VarBC now more space for observation forcing, allowing it to more strongly moisten the low-level troposphere. So in this, in these plots, we can see that both experiment does moisten the low-level troposphere compared to control simulation, which is good. But this is only for low level. Here we look at the whole atmosphere. So we look at the zonal mean humidity difference of analysis to and 1 to 3 day forecast compared to control run. And here x-axis is latitude, y-axis is height. Left panel shows the clear right panel shows clear cloud experiment. We see that the moistening is widespread and fairly uniform in space, likely because most of the changes comes from the change in global offset. However, this change seems to only improve the humidity in lower troposphere. So here we show the scorecard of different variables and compare to Era 5. Unfortunately, red is opposite for COSO's scorecard. Red means degradation. So it means that except for low level humidity, most of other variables degrade compared to control run. And I didn't show it here, but further examination show that this excessive humidity increment leads to degradation in temperature and wind forecast. And it suggests we probably need a more state-dependent humidity increment. So next, we explore the effect of adding cloud predictors to the clear cloud experiment. So
just to say, Chih-Chi, there's about 2 minutes of presentation left if you want some time for questions. So.
Okay, thank you. Okay, so yeah, maybe I'll perhaps skip a little details here, but essentially, first of all, we tried the polynomial form for this cloud-dependent bias correction, but we do found some issue, and we found that this is because the or maybe I can explain this later if everyone is interested, but so what we propose instead is to use a more non-parametric way to parameterize this cloud-dependent bias correction. And I'll skip this for now and look at the result here. So here we look at the total bias correction as a function of cloud amount, and the black for control, blue for clear cloud, and green for with cloud predictors. And we see that for clear sky, the total bias is smaller, while for cloudy skies, it becomes larger. And as mentioned earlier, because of the observation error variance normalization effect, for samples with larger cloud amount, the actual impact is smaller because of this normalization. So we actually quantify this effect. So as expected, for larger cloud amount, although the bias is quite different, but after this normalization, the observation forcing is quite similar between all the experiment. On the other hand, for the difference actually show up in for the samples with smaller cloud amount, and this may have significant impact because the number of samples are much larger within this cloud range. So yeah, the takeaway of this plot is that we found that adding cloud predictor moistens the troposphere under clear sky conditions, but dries the atmosphere under cloudy sky conditions. And we found that this does mitigate the temperature degradation that we found without cloud predictors, suggesting there are some benefits adding cloud predictors. And it also improves the median range forecast compared to clear cloud experiment. And lastly, we further do another experiment that only focus on this proposed change on lower peaking channels, and we found further improvement over the original experiment where the changes are applied to all the all sky channels, including humidity and temperature sounding channels. Okay, so I'll leave my conclusion here and take questions. Thank you.
Great, thanks very much indeed, and really interesting presentation. And we've got one question in the OPAD, which is from Prashant, which is, how do you confirm that the background error covariance B and the beta 0 error covariance are independent in variational techniques?
The background error covariance and
It's basically about the background error independence between the bias correction background error and the geophysical state background error.
Yeah, it's a great question. Yeah, because based on the can you still see my screen, or?
You can see the minimized presentation now.
Okay. Yeah. So currently, the formula that we use assumes that these two are independent. But Yes, I think this is a great question. I don't have a good answer for now.
Okay.
Yeah.
All right. Anyway, thanks for the answer, and we'll end keep on time. We'll end there. Thanks very much indeed again, Chi.